speaker for today is Professor Alexander Goncharov from Yale University. So Sasha, I believe, began to attend the Gelfand seminar when he was a freshman. Yeah, correct? Correct, okay. And so this is, oh, sorry. And so his talk is...
I'll do it.
Okay, so his talk is about geometry of canonical bases and mirror symmetry.
Thank you very much. Thank you very much for invitation. I'm very glad to be here. As Volodya said, I'm a Gelfand student and owe a lot to Israel Message as a mathematician and as a person. My talk is a joint work with Linghui Shen, who is a graduate student at Yale. And it's on geometry of canonical bases and I would say homological mirror symmetry. So, as Israel Message always taught us, we should start with an example. So let me start with an example which is simplest for the kind of examples I want to consider. So let's start with the surface S. So let's suppose we have a surface, topological surface, oriented surface with, for now, maybe cusps, later on maybe holes. And so that's S, a surface. Now we have attached to the surface the modular space of local systems, SL2 local systems on this surface. SL2 local systems on S. It's a stack, it's a modular space. And then I want immediately to introduce some data which I need, which is called lamination. So lamination is geometrical data. It's a collection of curves like that. And so I call these curves, so again, I'm given a definition. What is an integral lamination? On S. It's a set, they form a set. And to get an element of the set, you take a collection of loops, alpha 1 and so on, alpha n, which are simple, right on the picture, closed loops which are not intersecting, not self-intersecting, and not isotopic. And you attach to each of them some multiplicity. Let's say this is multiplicity k1, this is k2, this is k3. And so we consider kind of formal linear combination of isotopic classes of these loops with those multiplicities, where these integers multiplicities are integral and positive. And we consider these collections modular isotopy. And so I just want to write that the key assumption about this is that they are not non-self-intersecting and simple. Self-intersecting and simple loops. This is the alpha i's. So I said mutually non-intersecting. That's what I mean. Sorry, I mean not intersecting and not self-intersecting. Like that. Thank you. Now the point is that we can assign to such a lamination, let's call it L, a function. So each L give rise to a function which I call ML, which is a regular function in the space, in the modular space of all local systems on S. Now, how we construct this function? So this function ML, it takes a local system, L, which belongs to this modular space, and it assigns to this local system a complex number. So this complex number is given by the product of the following. So first of all, you have your loop alpha. That's called alpha I. Then you can consider monodromy, operator of monodromy around this loop alpha I. Then if your loop alpha I has multiplicity ki, you can raise it to this power. You get power of this monodromy map. Then you can take a trace of this, and you get a complex number. And finally, you take the product of all these numbers over all entries of your elimination. In this case, you have product of n numbers. So that's obviously a regular function on the space of local systems. And the theorem tells you that that's a canonical basis. That's a basis called canonical. So this is theorem which we actually were proving in situation and defining, which is more general than what I consider. In our situation, we also allow surfaces to have holes and some points on the boundary. We'll get to this. But for now, this is the theorem with Volodya-Fock says that this collection of functions is a linear basis on or in the space of all local systems on SL2S. Now, as I said, a similar story is true in more general situation. Let me just introduce the topological derivative which need to this. You can consider a surface like that, which has holes on the boundary, and in addition to punchers, and you can put some marked points on those holes. Punch itself, consider it as a kind of special point. And you treat this topological data modular isotopy, of course, and one can call this decorated surface. And so what would be nice to do is, let me formulate this as a goal, you can just take the modular space, we generalize the notion of modular space of local systems, not exactly local systems per se, which is related to arbitrary group G and this decorated surface. You can have functions here, and you want to have some basis in this space. Now, let me say from the beginning that G in this story is a split semi-simple algebraic group over Q, SL2, for example. And so that was an example of this canonical basis. Now, talking about canonical basis in general, first of all, the very idea that there is some special basis in representation is strange. And the first example was given by Gelfand and Zeitlin. They have two papers in 1950. So I wouldn't call them canonical, call it special basis. Then skipping a long story, let me get to the main points, that there was a canonical basis of Lustig. So it was the work of Lustig and also the work of Kashevara on crystal basis. This is end of 80s. Let me put something like 9, something like that. And so it's very strange that you have some distinguished basis in a vector space, but in this case, this is, for example, canonical basis in the following. Take representation V lambda of G, for example, and you're interested, you decompose this as direct sum of weight subspaces, and Lustig had canonical basis in this vector space with this data. And what he discovered, not only that he had a basis, he had a way to parameterize this basis. And so in Gelfand-Zeppelin case, this was this famous Gelfand-Zeppelin tableau, which is a collection of integers. So that's how we usually define sets. By collection of integers, it finds some properties. In the case of Lustig, it was a set which was defined in a more sophisticated way. And what he discovered, Lustig, is two things. I mean, many, but the two are most important. that first of all, the Lagrange dual group appears in description of parameters of this basis. And the second thing, he discovered that the total positivity matters. His paper in 93 about total positivity in Lie groups, that these two structures are somehow related to the canonical basis of G. Again, I emphasize, you start from G, you construct canonical basis in vector space of G, but the Lagrange dual group comes, and that's very surprising. And some other structures, which allows to construct Lustig set parameterizing the data. Okay, after this little historical comment, let me go straight to what I'm talking about. So, and let's consider the next example. So this example will be when my surface is a disk. This will be the main example for today. And this disk comes with a collection of n marked points, modulo isotopy. And so we want to have some space, some base in this space, and so on. So first of all, we start with what's called principal affine space A. It's just G mod U. U is a maximal unipotent. It's isomorphic to it. And then it, of course, projects to the Flach variety B, which is isomorphic to G mod B, where B is a maximal solvable subgroup, Borel subgroup. And this guy is defined better. It is actually the set of all Borel subgroups in G. And if you use one of them, B, then you can identify it with G mod B. With G mod U, it's a little worse, because you can parameterize this as a modular space, not just as a coset, which is misleading, only in the assumption that the center, I mean, you can do this easily when the center of G is trivial. And so if you assume this, then this principal affine space A, and that's very important for the future, is a modular space of pairs which consist of unipotent subgroup, maximal unipotent subgroup, and a character. So U is a maximal unipotent in G, and chi is a character from U to complex numbers. So it's additive character, not to Gm, but to C, not to C star, but to C. And it's non-degenerate. So non-degenerate, for example, means that the Cartan group, which acts naturally on U, acts, they form single orbit under the action of the Cartan group, and this orbit has dimension of Cartan group. And in simplest possible example, you just take matrices like that, and they go to lambda A, and this lambda is not equal to 0. That's the parameter of the character. Okay, so that's the A. And, sorry, one more thing I want to say, that if you take the A for SL2, then this is just C2 minus 0. Keep this in mind. Now, let's consider the configuration spaces. I mean, talking about canonical basis, let me stop here for a second. Of course, there is no canonical basis in representation per se, because if you take GLN and take a vector space, there is no canonical basis in a vector space, no matter what you do. But what, yeah? No, it's algebraic group. I can take it, and I speak about algebraic varieties over cube by means of their complex points, which is totally adequate. So it's A2 minus 0. But, okay? So again, so if you take, for example, GLN, there is no canonical basis. But what Lustig did, he said that if you choose basis in one representation for GLN, like basis in using vector space, means you use some standard data for the Lie group, then all representations suddenly acquire canonical basis. And in the example I give, there was no choices whatsoever. So this is just with a space, and space has a basis. And again, the point was that the space which parameterized this canonical basis was kind of funny space. It was a space of laminations. So the very word lamination, in the case when the surface has no punches, for example, this is the standard definition of Thurston of what is integral lamination. So this is a Thurston's laminations on S. So they somehow related to the question of canonical basis. Okay, now let's do this case, and let's consider the main hero. This is a space of configurations of n points in the principal affine space, which is, of course, defined as A to n modulo the action of the group G. So that's a stack. Its generic part is a nice fine algebraic variety, but that's a kind of stack. And I want also to have description of this fellow in the simplest example, where you take conf 2 of A. And I want to consider only generic part of this stack. I put here cross, which means this is the pairs of decorated flags. I usually denote them by A's, such that if you consider the corresponding Borel subgroups, remember it has this projection, then this pair of Borel subgroups is generic, means it belongs to the biggest Bruchas cell in B cross B. Now, it's very easy to see, and it's crucial for me, that this space conf cross A is actually canonically identified with a Cartan group. And so I'm going to use this invariant many times. So for example, for SL2, it just says that if you have two vectors, V1 and V2 in two-dimensional vector space with a volume form in symplectic structure, you can create a number which is just the symplectic area of the parallelogram generated by these two vectors. And the number is not 0, that's what we claim here, if they are in generic position. All right, so I'm going actually to denote these pairs of affine or non-decorated flags in generic position by this picture. So I put here little edge, put two decorated flags here, and put dotted lines. Punched line means that they're in generic position. Now, if you consider the general situation, if you have n decorated flags, then, for example, picture like that, then you can put here A1, A2, A3, and so on. They're all in generic position, AN. And what I wanted to do, I wanted to define a function, which is key player, which is a potential. So this is going to be a function, W, which takes the space conf n cross A just to complex numbers. I mean, it's a regular function which over a field of complex numbers does just that. So now how do we do this? So in the language of pictures, we do the following. Let's take one vertex of this polygon where we have some kind of decorated flag sitting. And so in large scale, it looks like that. So we have AI, it's a decorated flag. And then we have also BI minus 1 and let's say BI plus 1, which are Z flags which correspond to these decorated flags. And then there exists unique element of the group which moves them. And the key remark is the following, that if you consider pairs which form generic A and B's like that, then this is principal G space. So the group G acts simply transitively on this space of generic pairs A, B. And therefore, there is always element UI which transforms this frame to this frame. But now remember that this AI is a pair. It consists of unipotent subgroup, which we call UAI, and of a character. So now we got some element UI, and it's very easy to see that this UI lives in this subgroup because it preserves this flag. Therefore, we can take the value of the character which is assigned to my decorated flag and evaluate this character on the element UI. We get a number. Now we can take the sum over all vertices of my polygon And so this gives you the definition. This is by definition the value of the potential on the collection A1 and so on AN. All right. Now, let me give you some examples. So let's suppose, so I'll do it here, that G is SL2. And let's suppose that n equals 3. And so in this case, I'm talking about just triple of vectors, which I can call V1 and V2 in V3 in a two-dimensional vector space. And so the number I attach to them is given by the following formula. Let's say that delta 1, 2 is the area of the parallelogram generated by V1 and V2. So you consider the following funny expression, plus cyclic shifts, delta 2, 3 over delta 1, 2, and delta 1, 3, plus delta 1, 3 over delta 1, 2, and delta 2, 3. And you say that, for example, this term is what you get, which corresponds to precisely this vertex. So the function I just defined for this specific vertex is calculated in these terms. So that's the simplest possible potential in the world. Now, what's a little bit more complicated potential? Let's suppose that we have 4 points. 4 vectors in a space. What? It's a, so I use chi, so that's the definition. There is no delta. So I'm talking here about SL2. The group SL2 is a group of transformation of two-dimensional space with a volume form, symplectic form. Using the symplectic volume form, you define delta ij to be the volume of the parallelogram spanned by these two vectors. Okay? Now, let me give you one more example. So if you take n equals 4, then you're talking about configuration of 4 vectors. And so you have V1 here, V2, V3, and V4. And now if you use a diagonal, you can have 5 functions, these deltas, on the configuration space. And so the whole configuration space, conf 4, in this case, is just polynomials in all possible delta ij's. There are 6 of them, which corresponds to 2 diagonals and 4 edges. And there is only one relation, the famous one, the Plücker one, delta 1, 2, delta 3, 4 plus delta 1, 4, delta 2, 3 equals delta 1, 3, delta 2, 4. That's description of the space of functions. Now, potential related to this quadrilateral, you can define as taking the potential related to upper triangle and adding this potential related to the bottom triangle. It turns out that's what the general definition gives. Or you can do it by using another triangulation. So now in this case, you get something like that. So it's independent. It's a canonically defined function. Now, talking about these spaces, you see that in this particular case, it is defined as a quotient of the ring of polynomials by some ideal, which is used defining only the addition, no subtraction. And that's a general fact. So which goes to the same circle of ideals, that if you consider this moduli space, configuration of n affine flags, then it has a positive structure, actually cyclically covariant positive structure. And so this is a similar thing to what to total positivity which Lustig was doing, but in a different situation. So the same kind of structure. And yes? Equal. It's an, I mean, oh, okay, take minus, come on, take minus 2. But I prefer to write the equation this way. Yeah. So I consider this given as this equation. So I said this is the polynomials in these variables, and they satisfy this equation. The equation does not have minus. That's all I mean. Okay? No, it doesn't. So you see, no minus. So You will see how it works in a second. Ilya, you will see how it works in a second. We have no questions. So the point is that if you really want to do it slowly, you want to say that you have two coordinate systems here. One corresponds to this diagonal, and the other corresponds to the other diagonal. And what you really do, you write the equation that the second coordinate, delta 2, 4, is this plus this divided by delta 1, 3. Now, this equation is perfectly subtraction-free. And that's all I use, OK? No minus signs. All right, so the fact is that this potential is a positive function. And so we can use the whole little machinery of what we can do with positive functions on positive spaces to create some nice objects, which are going to parameterize canonical basis. So it's a general fact. So let's suppose that we have a positive space. X is a space with a positive structure, which means that space like that it has lots of coordinate systems and they are related by subtraction-free formulas. Then, first of all, we can define the set of tropical points of this space, which is isomorphic to many, many different ways to z to the dimension of this space, x. Each coordinate system gives you such identification. Secondly, if this w is positive, then you can tropicalize it and get a function, tropicalized w, on the space of tropical points, which I just mentioned, two integers. That's a tropicalization positive function. And finally, and most importantly for us, if you have a pair which is given by a space and a function, you can consider a set, that could be called xw plus of zt, which is just the collection of all tropical points, which has the property that the tropicalized potential on these points is non-negative. So that's the main point, that the space with potential give you a subset. That's the main message, that we have space, we have potential, we immediately have a subset. Now, how this subset looks like in some examples. So for example, what happens if my space is a torus? Just split torus. Then it's positive space for trivial reasons, just have single coordinate system. And in this case, the set of tropical points, by definition, if you want it, this is just the set of co-characters of this torus. Home from GM to H. Now, now I'm ready to formulate, to get to the formulation of the main result. So you see, we have a space, which is a space of generic configurations of n points of the principal affine space. This space has a positive potential, which I just introduced. It also maps canonically, that's a map pi, to the nth power of the Cartan group. And the map is obvious here. For example, here you just assign to this edge this invariant alpha of alpha 2, alpha 3, which belongs to the Cartan. So the Cartans are sitting over the edges here. That's where the Cartan's sitting. On the other hand, you can tropicalize this whole diagram. And so you get a set which we denote conv n plus a zt, a little complicated notation, but let me keep it. And this set maps by the tropicalized projection to the set of co-characters of my Cartan group, which I denoted to P. But actually, you can prove that it maps to the lattice of dominant weights. So this P plus is dominant weights for the Langlands dual group, which means characters of the original, co-characters of the original group which lie in a cone. So let me not spoil this diagram here. So we have such a data. Now, if you choose some element here, collection of dominant weights, then you get some subset here as a fiber. And so now the theorem says that's exactly the space which parameterize what we wanted, which parameterize the canonical basis, in this case, an invariance of tensor products. So, theorem that if you take the fiber of this tropicalized map on the left and take preimage of a single point in the base, I say that this set, so it lives in conv n plus AZT. And so the theorem is that this parameterizes a canonical basis in where? In invariance of tensor products. So you take V lambda 1 tensor and so on tensor V lambda n, and you take invariance with respect to the Langlands dual group. Now, actually, it's more than just theorems and it's parameterized something. It's a construction. And that's what I'm going to explain right now. That there is a construction which tells you how to construct the basis. And actually, it's kind of universal and very simple. Universal means that this is only example related to a very specific surface. Remember, this is a theorem about the disk only. And there's a construction. So let me explain now this construction. Before I go, let me go back to the history. So there was a Lustig canonical basis in representation, and Lustig constructed canonical basis here as well. And that's not going to be exactly the basis which I'm going to produce by construction. There was another construction by Mirkovic and Vilonen. They have this MV cycles, Mirkovic-Vilonen cycles, which lead to some canonical basis, let's say, in this V lambda mu, in the representations. And so what I'm going to explain is that their beautiful construction is actually completely universal in a sense, and in particular, it works here and produces this result. So that's how it goes. So again, let's suppose that you have any positive space. And then let's take K as usual to be the field of Laurent polynomials in T. Then we have the following diagram. So, well, X is a positive space. I didn't say it's a space. It's something which glues from a tori. It's a birational object. There is no such thing as the points of the space, not existing. However, there is a smaller subset which we call transcendental points with values in K. It exists, and it sits in this non-existing space of K points, which I said this guy does not exist in general because we have no space in general, just only some charts. And then by construction, it maps by the valuation map to the set of tropical points, which is entirely well defined by the positive structure. And now the theorem says that it's actually a collection of some cells. And these cells are parameterized by the tropical points. So it's a little exercise in positive geometry. And I just want to emphasize that there is no space, but still there's such an object if you have no space. But it basically works as follows. Let me just do an example when you see the idea. So let's suppose that you want to do this for GM. Then in this case, you want to take generic transcendental points of GM of K, and they're given by the collection of Laurent series, AI T to I, where I starts from some number minus n. And the only condition is that this number minus n is a transcendental number. It's not in Q alg. It's a transcendental number, not algebraic. So, okay, that's a very trivial thing. You think you can just say take any kind of generic condition, and this works. It's going to work. There is a caveat. The caveat is the following, that there is a little theorem about this, that if you consider a positive map of two tori, which is a positive birational isomorphism, and you also require that the inverse map is also positive and therefore birational isomorphism. Then the sets which I introduced, transcendental points of K for one torus and the other torus, are actually identified by this map phi. Now, if the non-triviality here, a little non-triviality, a little salty, I would say, is the following, that if you want to consider the simplest possible example and take map phi, which takes x plus 1. That's a beautiful positive map in one variable, but it doesn't have this property. Because if you consider the sum of whatever generic you have series which starts from 1, it starts from t plus t squared and so on, and you put whatever conditions you like here, then you add 1, and you get 1 plus a1 t plus a2 t squared and so on. And this 1 destroys all your conditions because it's out of control. I can put here any number, and so whatever general condition you have, it seems to be destroyed. But the point is that the inverse swap is not positive. It has minus. So, okay, there is a little tool like that, which I'm going to use. And now we come to the construction. I'm going to construct cycles which, in particular case, which I probably will not discuss, will give you precisely MV cycles. So let me remind you that there is a space of frames. The frame for me is a data like that. You have decorated flag and the usual flag in generic position. And they form a moduli space, which I denoted by Fg. So this is a moduli space, frames like that, no quotients by the action of G. It's just a G torsor in G. Now, if you consider K points of this fellow, then I claim that there is a canonical map to the affine Grassmannian, which is defined as G of K by G of O. And the map is very simple. I mean, this pair AB, you can bring it to any lattice defined, let's say, over C, and then you can project to the affine Grassmannian. And it's G-torso, so there are no special points, but you can choose special points in this set of C points, and so your projection will not depend on this. Anyway, this is that way. There's a canonical lattice which corresponds to these frames. Okay, so if we are armed by this trivial remark, we have the following definition. Let's call a configuration of decorated flags in conf n A over the field K. Let's call them O integral, and that's a key notion which we use. It's O integral. If the following holds, if for any of these AIs, if it takes this AI and considers the corresponding lattice which corresponds to the pair Li, Bj for any j, this is independent of j. I prefer to think about things by pictures, and so I picture this as follows. So you have your polygon whose vertices gives you the affine flags, decorated flags. And then what you do, you take two of them, you take one of them, let's say this is AI, and you look at all other frames which you can see from this AI looking on any other different AJs. These all frames are different, but if you project them to the affine Grassmannian, it may happen that they're the same, and that's O integrality. So that's a condition. And again, if you just a side remark, if you think what it means in Archimedean situation, in SL2 you take hyperbolic plane, and then your A's are just horocycles, and your B's are just points on the boundary. And what you say that if you have horocycle points on the boundary, you have point inside, which is my lattice. But then the condition is that I'm looking on such triples, let's say, of guys, that these intersection points, they do not depend. So if you take this guy and look at these two independent points, they do not depend on this and this. Over real numbers, this can't never happen. This doesn't happen. And the point is that in Archimedean situations, there are plenty of examples, and that's where we go. So if you have these O integral configurations, then it's trivial from the definition that the O integral configurations project to the configurations in the affine Grassmannian, have canonical map from the set of these O integral configurations defined over K to the set of configurations of endpoints in the affine Grassmannian. And this is by definition just g of k divided by the Grassmannian to n. It's a canonical map like that. Just because when we take O integral configuration, A1 and so on, AN, we can assign to it the corresponding lattices, L1 and so on, Ln, which are defined, this is my lattice Li. It's defined by using the auxiliary flag Bj, but it does not depend on that. And therefore, we get a nice map of spaces from here to here. OK. Now, we can formulate what happens with... Now I can explain in one sentence how we construct the basis. But let me first formulate this. Not in one sentence, but a few minutes. So first of all, the main fact about this is the following theorem. What? B sub j is the usual flag which corresponds to the decorated flag A sub j. So we have the canonical projection from principal affine space to the space of flags. And if you take here any kind of AI, we associate to this projection BI. OK? Is that clear? Yeah? Now, let's suppose that we start with some tropical point in my configuration space over Zt. Then what we can do, we can take the corresponding cell. We have cell CL0. Because remember the setup. If you have any positive space and conf n is a positive space, then tropical points gives rise to decomposition of the set of these transcendental points into cells. And so we take one of these cells, and we intersect this cell with the O integral configurations. And then the answer, and that's the theorem, it's either the whole cell or it's empty. Now, it is the whole cell if and only if it's a positive tropical point. Means the tropicalization of my potential is non-negative, and it's empty otherwise. And so this conf O is somehow picks only cells which corresponds to positive tropical points. Now, finally, we can write one more diagram like that. I didn't actually give you a definition. I just said that there is a set of transcendental k points assigned to any positive space. And it maps by a certain so-called valuation map to a certain set of tropical points. Now, the fiber of this set, and maybe I didn't sell this, is by definition CL. You have a map of space, I mean, of huge set and a discrete set. The fiber is CL, CL0. Now, let's look again on what we have. So we have the space of all O integral configurations in the principal affine space. We have a generic part. It maps by this map kappa, which I just explained, just tautological map, to the space of configurations of endpoints in the affine Grassmannian. Now, here, we can take these cycles I called ML. This is a future generalized MV cycles, which is by definition, you take the image of your cell, CL0, and take it the risky closure. So you have some nice cycles sitting there, which you get just by transporting the points in this conf NA plus of ZT. So for whatever point here, you construct some cycle ML. Now notice that you must start here from positive tropical points, which are coded by this potential, because otherwise you get empty set. And actually, this is all the points which give you non-empty sets. And so the main theorem about this situation is that this construction describes you precisely the components of this stack. So the configuration of endpoints in the affine Grassmannian is a nice stack. And it has components, and it has top components. And so let me just describe them in the usual terms. So you have this convolution varieties. This is description of this stack. So the convolution varieties, let me call them gr lambda. They just described as collections of lattices. You take the trivial lattice, and then you connect them to some lattice L2, L3, L4. And connect means you have a sequence of n lattices, which means you have a subset in the product of n copies of a fine Grassmannian. Actually, it lives in just 1 cross gr n minus 1. And you require that the distances between any two subsequent lattices are given by the collection of the dominant weights for GL, which you specified. This is this lambda data. So that's a nice finite dimensional variety. And my stack actually is a quotient. So what I want to do, I wanted to take my conv and gr, and it has a component which has just the stack which corresponds to this. So I just take model G of 4. So this is the way you already see that this infinite dimensional configuration space of points in the affine Grassmannian is decomposed by the dominant weights for the Langlands dual group. Now, the main theorem about this situation is the following: that the cycles which we produce give you precisely the components. Well, that if you just consider the collection of the cycles which we produced in this specific situation, which are parameterized by the set Pt inverse of lambda, then this is precisely top components of this convolution stack gr lambda. And in this case, because it's basically variety modulo G of 4, it's clear what the dimension, what top component means. It's just top dimensional components of the convolution variety. So this result is similar situation was in Joel Kamnitzer's thesis, where he dealt with just single Grassmannian, and he gave some parameterization of MV cycles. And it turns out that this is just a special case of a more general phenomena, which I'm not going to talk about. But there is this is kind of general machine which produces you from positive tropical points components. And you can put all examples which appear in representation theory in this setup. So they obtained this way. OK, now why this gives you canonical basis? Because now there is kind of black box which says, as geometric Satake, which was due to Drinfeld, proposed in '86 and proved by Mirkovic, Wieland, and Ginzburg using the results of Lustig and other people later on. But it's a well-established fact that this top components of this convolution variety actually is the same thing as a basis in what we want, precisely in V lambda 1 tensor so on tensor V lambda n in GL invariance. That's what if you look on geometric Satake, that's what it would tell you. And so now you see that if you take, finally, you get this bijection which I promised. Because I wanted to construct bijection between this set and the canonical basis. And so summarizing all the discussion, I take this tropical integral point, construct the canonical cycle, prove that this is a top component of this Grassmannian, use geometric Satake, get basis. And I claim this happens in many other situations. All examples in representation theory, like canonical basis in representations, so in tensor products, they are obtained by a similar procedure, just varying the original positive space. But then the construction is identically the same. You just need to vary the positive space and the notion of what the Grassmannian is. OK. Now, let me just tell you that this fact already is not quite trivial, because what it implies, for example, for GLN, M, and n equals 3, there is another known description of the set of canonical basis, which is Knudsen-Tau honeycombs. And it turns out this is precisely these guys which we do here. Precisely means that there is a canonical bijection between these two sets, which uses a single specific coordinate system on configuration of 3 flags for GLM, which actually we constructed with Fock and Z activity a decade ago. So if you just apply this specific coordinate system, then the tropical points are coordinated exactly by the honeycombs. And so this therefore implies some conjecture of Kamnitzer for n is bigger than 3. He introduced some notion of what is analogs of Knudsen-Tau honeycombs, conjectures that there is some bijection between bases, natural bijection. So here we are, that's how this bijection is constructed, because the set of Kamnitzer again constructed using that specific coordinate system precisely this way. Okay, I wanted to go to mirror symmetry, but before I want to go there, I want just to mention that all this was just an example. The theorem about canonical bases, about components, which was the main backbone of this, happens in general. And what you do, you start with this decorated surface S, and you have arbitrary split group G. Then you can construct two moduli spaces. One of them generalization of the configuration space of affine flags, and this is moduli space of, roughly speaking, G local systems on S, plus some data on the boundary of S, moduli isomorphisms. And our construction immediately gives this space with a potential. The potential immediately generalizes to a function on this setup, on the space AGS, which is the analog of the configuration space at the same time it's analog of the local systems. Now also you can assign analog of the affine Grassmannian, which corresponds to the decorated surface, which again it will be moduli space of some G of K local systems on S, plus some data on the boundary. And again, in the case when your decorated surface is disk, you will recover the configuration space I worked with of n points in the affine Grassmannian. And so everything, geometric setup generalizes full steam to the arbitrary surface situation. And the theorem has an analog. Theorem says that if you consider the positive tropical points of the first space, it's actually top components of a stack of this spec GS, where I don't have time to explain what top component means because it's infinite dimensional stack, but the theorem works in this generality and produces some kind of basis on local systems on S. Now, I really want to go to mirror symmetry, so let's go there. Huh? Yes. When S is disk with n points, yes.
And if S is general, then...
So what the point is, okay, let me formulate this. I really want to talk to the mirror part. So the mirror, and you will see Volodya answer a question in a second. So mirror conjecture should say that the moduli space AG related to the surface S is mirrored with potential, which we constructed, is mirror dual to a similar moduli space, where here I need to put some kind of generic part here to make this function regular, as before, of something related to the Langlands dual group, and actually kind of dual surface, delta S, which is hard to distinguish from the original one. Now, in particular, your question, the answer is that if you take the tropical points here, plus with respect to this potential of ZT, this should correspond to the basis, it corresponds to some basis in the integral functions on this guy. Don't pay attention to the stars. Basically, it's almost the same surface. So the point is that this moduli space AGS, which is a space of configuration of n points in the affine Grassmannian, it turns out to be the mirror of itself if you go to the Langlands dual group. The point is that it's a mirror in the sense that this is space with potential. That's Landau-Ginzburg model, and that's the actual space. So they in mirror duality. And why I mention this? Because Volodya asked about the basis. And so in particular, if you look at this setup, if you take the tropical points of this space cut by the potential, then it should parameterize the basis here. Now the surface affine Grassmannian come as a third ingredient, which just allows you to go to components somehow. Okay, now let's go to the mirror. So Yeah.
What geometric
What?
What geometric, is, in order to define W, you need to draw something on the surface?
Nothing. If you have a surface with punctures, if you have a decorated surface, which is a surface which was drawn here, which has some boundary components on which you have some special points, and it may have some punctures, and that's it. If you just have that, then there is a moduli space, a moduli space, which is related to this, which I really briefly mentioned the definition. And the function W is canonical function in this space. So this is a Landau-Ginzburg potential. This space has Landau-Ginzburg potential. That's W. That's the point. Does this answer your question? I can tell you what the definition if I have more time. You just triangulate your surface into triangles, and then you use the same construction. You have for each vertex a fine flag, and you take the function which I constructed. For, let's say for each of the triangles, take a sum. It does not depend on the triangulation. Okay? All right. So why mirror? Now let's look what exactly the statement says. The statement says, the theorem that there exists canonical basis, says that there exists canonical pairing. Between a set, so it considers a set of configurations of n points in the principal affine space for the G, you take the positive tropical points, and that's a set. And the function is a map from this set cross the space of configurations of n points for a G for the Langlands dual group. There is a single function. Why there is a single function? Because this space parameterized basis in the functions here, because that's exactly the space of invariance functions here. And so if you give me any positive tropical point here, I construct here some function, FL here. Altogether, you can think about as a pairing. You pair tropical points with a space, you get a single function. Now, what is the tropical points? Remember, I started from laminations. So the general picture is the following, that if you have some positive space, then tropical points are points which live on some kind of tropical boundary. So they live here. And so what we do, we take one positive space for the group G, and we take essentially exactly the same space for GL, and it claims that on their product there is a function. But it pairs points at infinity here, in the example certain eliminations, with actual points here. That's very strange. Also, because the G and GL replace itself, you can treat it the other way. You can say that actually you start with tropical points here and pair with points here. So again, you have the same kind of situation, but you pair tropical to actual. And what's supposed to happen is that you have these two spaces, conf n a g, with potential. That's key here. Because not all tropical points, only the positive. So this Landau-Ginzburg model is supposed to be mirror to actual space conf n a for the Langlands dual group. Now, instead of formulating, I have like 2 minutes left, a precise conjecture here, I want to give you more things which we see from this point of view. So first of all, in some regimes you can prove this. In FOSL2 and some variants of this, you get to the statement you can check. But the most important point is that you not only have tropical points, you have the space of all positive points, conf NA, real positive points. That was original Lustig's total positivity. In this case, you get some subset. And so now this guy, and you also have potential, and you also have the volume form, which I don't have time to talk about, but in each of the coordinate systems is just d log of A1, which and so on, d log of AN. That's the volume form which we constructed with Volodymyr in general situations, the cluster volume form. So you have this triple. Now, if you have this triple, as Maxime explained, there is a special Lagrangian. Some variety corresponding to this. And so actually what happens is that not only you have equivalence of categories, so here you're supposed to put Foucault. I mean, this is not the actual formulation because I'm lacking some precision. Foucault's idle wrapped categories should correspond to, let's say, dB Koch here, or vice versa. But under this, for example, correspondence, this positive A brane, which means this conv n of A of R plus, should correspond to structure sheaf O. Now, more than that, because you have the potential, and I'm finishing then, allows you to write down some functions which you can treat as stabilities on Fukaya-Zeidel categories, which I believe is these good stabilities of which Maxim was talking about. Most generally, you can just start writing oscillating integral, but to do better, we have this conv NA. And remember, it maps by pi to the h to n. And we can take the fibers of this projection. Let's say we have some point here. And we can take some character, for example, of this torus. So we can start writing integrals something like character multiplied by the exponent of minus potential divided by the Planck constant, volume form on the fibers. And so we get some function which may depend on the points on the projection and also on some characters on the Planck constant. So this should give you, this is the central charge. This is Z. The central charge which Maxim was talking about should be on one hand side, and I'm really finishing now. On the other hand, since the picture is completely symmetric, so before I'm talking about taking A model here and B model here, now I can take B model here, A model here and B model here. And in this case, we still have exactly the same function, but the meaning will be different. The meaning this time will be that this will be, in some situations, I have to decide, tell you precisely what's going on. It's now extremely rough. But basically what happens is that exactly the same function tells you the solution, this given Thales J function, solution of the corresponding variation of quantum connection on this side. So now this will become A side. You have quantum connection here. And the same function solves this function connection. And finally, this tori is extremely important. And so this mirror symmetry is not actually supposed to be mirror symmetry about the spaces. It's supposed to be mirror symmetry between the stacks. And this really happens. And if I had more time, I will explain how this works, for example, for flag varieties, where in the simple possible case, it provides a description. Take dB Koch C star equivariant on CP1. And if you run all this machinery in slightly different example, which is exactly canonical based example, this is Landau-Ginzburg model for C star and Z plus 1 over Z. And you can put here some complex number A, which doesn't change Fukaya-Zeidel category. So the equivalence in between Fukaya-Zeidel rep of this and that. And so this gives you the stability. And it also explains, so here, that's, you have to take not C, I'm sorry. Okay, this is the last thing I'm saying, then I'm stupid. But I need some space. Let me just formulate one statement, but formulate it precisely. So you start with dB Koch C star equivariant sheaves on CP1. On the other side, you get Fukaya-Zeidel, not on C star, which is supposed to be mirror Zul, but on its universal cover on C. And the potential you get is exponent of T plus exponent of minus T. And so that's one of the equivalents. The point is that if you want to do the mirror symmetry of the stack, so this is a stack in this situation, then you have to go to some covers of the original space you thought were the mirrors. And then you see that in this case, there is a Z plus Z, which is precisely the Picard group of this stack, CP1 by C star. And you can see geometrically how the Z plus Z X and Fukaya-Zeidel categories very, very simple way. Just as Maxim explained, when you go to Fukaya, some usual geometry becomes very transparent, but you have to do some modification. You have to modify your original space and construct some universal coverage, no longer complex space and so on. So that's it. Thank you very much. I didn't have time to mention that there is one more thing about this. Okay, let me stop here. There's just a set of mirror conjectures related to very general Calabi-Yau due to Kiel, Gross, and Hacking, which is closely related to this. On one hand side, it's more general because it treats any Calabi-Yau. On the other hand, it doesn't have explicit description right hand side and some other ingredients like the potential. And there's going to be proof soon, I believe. But it's kind of going in different directions, and it would be interesting to see how it goes together.
So let's count this as an answer for my question. So are there any other questions?
Is it true that these bases that you construct are well compatible with quantization of these modular spaces, connections?
I think it's going to eventually be true. It's not part of the construction at the moment, but I think that's supposed to be the case. But
for example, when you have a tensor product, this also works for quantum group. And spaces have quantization, and should be compatible.
We had with folks these duality conjectures which go into quantum situations, and this is just some examples in that situation, but it's not a theorem.
So canonical bases have been connected to quantification.
Yes.
Is it?
Great question, because what you see here, you see that you have this A brane, which should correspond to the sheaf O. If you want to get canonical basis, you take the Hom from O to O, which means you take the Hom in Foucault-Seidel from here to here. That's where your canonical basis sits. And so this is a space of parameters. Now you're talking about categorification of this Hom. This means that there should be some kind of two category which lives over the usual categories like Foucault-Seidel categories. I have no clue, but that's what it should look like.
Other